All right, for Chapter 12, Section 3, we're going to look at the dot product. And the dot product you can use to find the angle between two vectors. You can use it to find the projection of one vector onto another, things like that, so it can be very useful. But the first one where it says find the angle between the vectors, and it's going to break it down into the component, so it's going to do step by step. So the overall formula is right here. The angle between two vectors is the ratio of their dot product to the multiplication of their two magnitudes, and then you take an arc cosine, and that will give you the actual angle. So let me actually draw this. So what we're imagining is we have two vectors, and usually we imagine that they are touching in some way. So we have A and B. Let me do lowercase like they use. This is the angle between them. So that is what we're solving for. And you could plot these, like if you had graph paper, you could plot these two vectors and you could estimate it graphically, but we're just going to do the arithmetic. So the first thing they're going to have us find is the magnitude of each vector. So the magnitude of each vector is the components squared, so 2 squared, minus 1 squared for A, and then you take a square root of that. So it's like the Pythagorean theorem. And then for B, you take, it's actually not Pythagorean theorem, but it's like that. You square the components, add them up, and take a square root. So then for B, it's 3 squared, minus 1 squared, and 3 squared again in 3 dimensions. And so you'll get 3 and square root of 19 when you do this. Now the dot product, we saw this last time, would be 2 times 3, so we get that here, plus 2 times minus 1, so we get that here, plus minus 1 times 3, which we get here, so it's 6 minus 2 minus 3, you get 1. Okay, so that dot product goes on top, this 1 goes here, then these two numbers multiplied go right down here. Okay, so that's the ratio. Then the final step is to take an arc cosine of that exact ratio. Now be careful, use radians on your calculator. You should get 1.49 radians, which is about, actually let me figure out what that is. That's about 85 degrees. So just shy of 90. The angle between these two vectors would be 85 degrees. So that's problem 1. That's problem 1. Just got to follow those steps. Kind of lead you through it step by step. Okay, problem 2 is really similar. So this is going to be a scalar projection of vector B onto A, and then the projection of B onto A, the vector projection. So there's two projections here, the scalar projection and the vector projection. Now, because this is in 3 dimensions, I'm not going to try to draw it. It's we've actually got a picture later where we'll see what it represents in 2 dimensions. So let's kind of put a pin on what the scalar projection and the vector projection is until we see the example problem with the computer-generated diagrams, because these are very hard to draw. But let's look. The scalar projection is you take the dot product of the two vectors divided by the magnitude of one of the vectors. So to do this, I don't think there's anything that you have to do except for do the dot product here. So you do, let's see here, we have 1 times minus 1, so it's minus 1 plus 1 times 4 is 4, so we're at 3 now. And then 2 times 3 is 6, so we have 9. So this whole dot product is just 9, and then the magnitude of A, they just took minus 1 squared, 4 squared, 3 squared, add them up, and they got square root of 26. So that's the scalar projection. Scalar is just a number, so this is just a number. 9 divided by root 26 is some decimal value if you wanted to get it. Now, the vector projection takes the scalar projection, that 9 divided by square root of 26, and then you multiply by the vector A divided by its magnitude. But we already know that the magnitude of A is square root of 26. So part of this equation, part of this calculation, is the square root of 26 times the square root of 26. If you have the same number square rooted and you multiply them, the square root just goes away, so you're left with 26 on the bottom. And then A, we haven't plugged in yet. They just wanted you to see that this 9 is going to carry over, and this root 26 times root 26 would form just regular 26. Then you have to multiply that by A. So what we got, let me actually show you this part. So this would be, to get to this answer here, you would take 9 over 26 times the vector A minus 1, 4, and 3. So you're going to get 9 times minus 1, which is minus 9, all over 26. You're going to get 4 times 9, which is going to be 36, but let me show you that step. So 4 times 9 will be 36 divided by the 26. You can divide both those by 2 and you get 18 over 13. So that's how we got that number. And then 3 times 9 would be 27 over 26, gives us that third one. So that's how we got those steps there. So still I would consider these to be pretty straightforward because you're not doing anything other than kind of following what they want you to do. Okay, let's look at problem 3 a little more closely. So when you take a dot product, you get a number out. It's called a scalar. It has, it could represent length of something or how much we're stretching or shrinking something, but it just represents a value. A vector has a length and a direction. So it has an angle and it has a length. And what you can't do is, there's many operations where you can't do scalars and vectors. They might not mix. So let's look at when that would happen. So in this it says A dot B, which is a scalar, dotted with C. So you can't take a scalar dot product a vector. So that doesn't work. Now there's a subtle difference here. You can take a, let me not use red. You can take a scalar times a vector. So if this is times, that one's okay. But if it's a bigger dot, usually it's a bold dot, this is dot product. Dot product is only defined when you take a vector dotted with a vector. You have to have two vectors. So this one has no meaning because you're doing a dot product of a scalar and a vector. Okay, now let's look at this one. B is what I just showed here. A dot B is going to be a scalar, and then when they don't write anything in between, it's assumed multiplication. So this one would be scalar times the vector C, and that one is okay. So that has meaning, and because you're taking a scalar times a vector. And we had seen this, so if I have vector B, 2B of scalar times that vector would just double its length. So now it's twice as long. That one's fine. Okay, C, we have the magnitude of A. The magnitude of A is a scalar. A dot B is a scalar. And a scalar times a scalar. And I have to be careful here. This is times, not, in fact, let me not use that. Let me use the little x here. A scalar times a scalar is fine. That's like 3 times 5, 15. No problem at all. So this one has meaning because it's the product, not dot product, the product multiplication of two scalars. Okay, in this one, we have B plus C, which is a vector. So adding two vectors gives us a vector. They're using dot product, and A is a vector. So we have vector dotted with vector. That is okay. So that's where you take the first numbers multiplied, the second numbers multiplied, and the third numbers multiplied, and add them all together. So that's fine. In this one, order of operations says we would do left to right. So A dot B is going to give us a scalar. Then we're trying to add this to a vector. This one is not okay. So it does not have meaning, no meaning, because you can't add a scalar and a vector. You can only add vectors and vectors. So you can do scalar plus scalar. Scalar plus or minus scalar. That one's okay. You can do vector plus or minus vector. That one's okay. But you can't mix those two up. You can't do scalars and vectors or vectors and scalars when you're adding or subtracting. Okay, last one. Magnitude of A is a scalar. B plus C is a vector. And they're trying to dot those two. That one's not going to work. Okay, so that one also has no meaning. So we have to be real careful with scalars and vectors. There's some things we can do, there's some things we cannot. Okay, for problem 4, it's a force problem, work actually. So work is equal to the force vector, we've actually seen this before, dotted with the distance vector. And they gave us a force vector. Notice this is a dot product, so work is going to be a scalar, just a number. The force vector in this problem is 4 in the I, minus 6 in the J, and 5 in the K. So 3 dimensionals dotted with. We have to find the distance vector. The distance vector is just the difference of these X, Y, and Z numbers. So we're just going to do 6 minus 0, 16 minus 6, and 18 minus 6. Now again, you could plot those 2 points in 3 dimensions and see how they look, but 3-dimensional drawing is hard without a computer. So let's just look at it as numbers. So 6 minus 0 is 6, 16 minus 6 is 10, 18 minus 6 is 12. Now when we dot this, the work is going to be 4 times 6. So again, we just dot the first, we multiply the first two, 4 times 6, plus multiply the second two, minus 6 times 10, and then finally multiply the third with the third, plus 5 times 12. Now this is kind of nice. You get minus 60 and plus 60, those cancel exactly. So the work is just 4 times 6, 24, and the units are joules. So force, let's talk units. Force is in newtons. Distance is in meters. And when you dot those two, you get Newton times meter, which the international standard for that is called a joule, or J. Okay, and that would be problem 4. Problem 5 says find A dot. I mean, this is like a problem we could have done right away. This is very simple. You're just going to take A dot B is equal to minus 1 times minus 3 and a quarter times 16. So you get minus 1 times minus 3 plus a quarter times 16, positive 3 plus 4, and it's going to be 7. So that one I would consider to be very simple. This one's also not too bad. It's very similar, except they're using letters. So the dot product of these two would be P times 5Q, which would be 5PQ, plus minus P times Q, so it's going to be minus P times Q, plus the third term would be 9P times minus Q, minus 9PQ. And they all have the same appendix, PQ. So we have 5 of them, minus 1 of them, minus 9 of them. So we have 5 PQs minus 10 PQs, which would be minus 5 PQs. And that's what we get there. So problem 6. So those two problems I would not consider to be very difficult. I would anticipate if I gave these to you on a test, you should be very quick with those. Okay, problem 7. It gives us the magnitude of the vector A, the magnitude of vector B, and the angle between them. So we have to use the fact that the cosine of the angle between two vectors is equal to A dotted with B divided by the magnitude of A times the magnitude of b. Well, we actually know theta, a, and b, so we're solving for a dot b. So we just have to rearrange this formula ever so slightly, multiply both sides by the magnitude of a and the magnitude of b into the cosine of theta, and that will tell us the dot product. So we just have to plug in our numbers. Magnitude of a is 7, magnitude of b is root 6, and the angle is 45 degrees. Now this, from unit circle, because your calculator probably won't give this to you in exact form, so if you go to unit circle from our trig memories, and you look up 45 degrees, you will see that cosine is root 2 over 2. So what we get is 7 times the root 2 times root 6 is root 12, all over 2. 12 can be written as 4 times 3. And the 4 will come out of the square root as a 2. So it's 7 times 2, root 3 over 2. Those 2's will cancel, and you get 7 root 3. So that would be the dot product of those two vectors. Notice we didn't even know what the components of the vectors were. We just knew the angle between them and their magnitudes. Okay, problem 8 might be tricky if we don't remember our trig. So it gives us three vectors, and it says they're all unit vectors. Now that's good to know. If they say unit vectors, they all have a length of 1. So this is like length 1, 1, and 1. Well, if we know a triangle has all the same sides, that's called an equilateral triangle, which means all the sides are the same, which means all the angles are the same. There's only one possible triangle that can have the same angle for every spot, and that's 60 degrees. Because those three angles have to add up to 180. Okay, so we know we're going to use the exact same formula, u dotted with v, and actually these are unit vectors, so I should use arrows above them, not hats, not arrows. U dot v is going to equal magnitude u times magnitude v times the cosine of the angle between them. Their magnitudes are 1, so that's easy enough, 1 times 1. And the angle between them is 60 degrees. And you can look up 60 degrees on unit circle, it is 1/2. So we get 1 times 1 times 1/2, so the whole thing is just 1/2. Now that's u dot v, that's these two right here. Now it gets a little more interesting when you have u dot w, because their tips and their tails don't line up right. So if I line up their tips and tails, u goes down to the left like this, w goes to the right like that. Well, this actually now becomes double 60. This is now 120 degrees. So this is u, this is w. Otherwise, the equation stays the same. It's magnitude of u, which is 1, times magnitude of w, which is 1, times cosine of now 120 degrees, the angle between them. And this will be -1 if you look at unit circle, which reduces to -1/2. Excuse me, -1/2, not -1. So cosine of 120 would be -1/2. Their magnitudes are 1, so the whole thing just multiplies to be -1/2. Problem 8. Okay, problem 9, they want us to find the angle between these two vectors. The first one they want us to be exact, and the second one they want to actually solve. So again, we're going to say if cosine theta equals a dot b divided by magnitude a magnitude b, then theta is arc cosine of a dot b divided by the magnitude of a times the magnitude of b, and we just have to find all those things. So magnitude of a is the square root of a's components, 7 squared plus 3 squared, which is the square root of 49 plus 9, which is 58, The magnitude of b, which is the square root of 3 squared plus minus 1 squared, is the square root of 9 plus 1, which is square root of 10. Now, a dot b, the top, the numerator, is going to equal 7 times 3 plus 3 times minus 1 21 minus 3, which is 18. And if you, so we'll get theta is the arc cosine of 18 divided by the square root of 58 times the square root of 10. And this is going to end up being, let's see, this is 2 times 9. This is the square root of 580, and it turns out that you can divide 580 by 4, and so you'll get the square root of 4 times 145. This 4 will come out as a 2. So it's 2 times 9, 18 on top. 2 square root of 145. Those 2's will cancel, and you'll just get 9 over the square root of 145. Then be very careful. You want to switch your calculator now to degree mode. And when you take the arc cosine of this fraction, you'll get 42 approximately after you round degrees. And that would be the angle between those two vectors. Okay, so for problem 10, you're going to repeat this. I'm not going to go through all this. Let me just do the first one. So we're going to look at, is it orthogonal, parallel, or neither? For orthogonal, theta would equal plus or minus 90 degrees. So we're just going to use that formula we just looked at and see if the angle is 90 degrees. For parallel, theta will equal 0 or plus or minus 180 degrees. And then for neither, well, theta is not one of these numbers. So for neither, theta is not 0 or plus or minus 90 or plus or minus 180. So it's not any of those 5. Okay, so we just have to go through and solve it again. So we would have, let's look at the first one, a dot b would equal negative 7 times 7, first of each, then the second of each, plus 5 times negative 6, then the third number with the third number, plus 4 times 3, and we're going to get negative 67. And then we'll find the magnitude of A, which is going to be the square root of minus 7 squared, plus 5 squared, plus 4 squared, and the magnitude of B, which is going to be the square root of 7 squared, plus minus 6 squared, plus 3 squared. And for those we'll get square root of 90 for A, which is 3 root 10, and we'll get square root of 94 for B, which doesn't simplify. So then, theta is the arc cosine of the dot product minus 67 divided by 3 root 10 times square root of 94. And we're basically just going to have to get this in decimal form. This would be, okay, and we plug this in as a decimal, 67 divided by 3 square root of 940. You'll get negative 0.7284. When you do an arc cosine in your calculator, be careful, switch to degree mode, you'll get 136.8. Now again, the only numbers we're interested in are 0, 90, minus 90, 180, or minus 180. It's neither of those 5, so we're going to click neither. Okay, now with 6423, let's actually look at that one because that one's easy to do. we can plot these two. There's 6. There's -2. There is 4. There is 3. So A is going to go from 0, 0 to 6, 4 to scale. That is vector A. B is going to go from 0, 0 to -2, 3, so right there. That is vector B. And if you do the equation, arc theta equals arc cosine of A dot B over A times B vector magnitudes, you will get that theta is 90 degrees. And that is called orthogonal. So, and we can see it in the drawing. So I drew it to scale, not too bad. So that is, you can kind of tell, those are orthogonal. Okay, and then if you do C, it's in 3 dimensions with the exact same approach. Those are also orthogonal. And then D, I wish I could draw better in 3 dimensions quickly. Basically, those two vectors, I can kind of simulate it here. Vector A is going to look something like this in 3-dimensional space, and then vector B is going to end up looking like this. And we're going to see, oh, the angle between those two is 180 degrees. These are called parallel vectors. Okay, so, but again, you don't have to draw these. The math will bear this out. So if you do the dot product of these two vectors, find their magnitudes, multiply those, take an arc cosine, you'll get either 0 or 180 degrees depending on, I'm pretty sure these point away from each other, but there is the possibility that blue points in the same direction as green, and it'll still be, this one would be 0 degrees. Either way, they're still parallel. Okay, so that's problem 10. Okay, for problem 11, it probably is useful to draw the picture, because you're given 2 lines. So you're given the equation of 2 lines. One starts at 7. And the other one starts at y value equal to, be careful here. Actually, shoot, I think I made the same mistake. Let's rearrange these equations. So this would be y is equal to 6x minus 4. And then the blue line would be y is equal to 8x minus 7. Just look at that quick and make sure that's right. No, that's not right. So good thing I looked. This is minus 8x plus 7. Okay, there we go. So this one is going to start at, let's start with the blue one. It starts at 7 in the y, and when, not a huge fan of this one, but so be it. When x is 7/8, which is just shy of 1, when x is 7/8, this will touch the y-axis. So this vector, this line, is going to go through these 2 points and down. Okay, that's the blue line. The green line is going to start at -4. So it's going to start down here. And when x is 2/3, it is going to cross, and boy, we have to be careful, these do not intersect. They're close, but they do not intersect there. Boy, it's tough to draw. It's going to look something like this. Okay, so let me blow this up with a better drawing. So green looks like this. Blue looks like this, and we're going to find 3 points. We are going to call, and I want to make sure I get this right, this is A, point A, and their intersection we're going to call point C, and then this point we're going to call point B. And so we're actually going to write these vectors like this. We're going to say from C to A and from C to B are the two vectors. Thus, this is the angle theta between them. Okay, so this point we know, point A is 7/8 in the, I did different, of course. Okay, so I did this slightly differently when I did it, so now I can't follow my notes. Okay, so A was 2/3, 0. B occurred at 7/8, 0. C, this is the tricky one. C occurs where those two are equal. So we're going to set 6x minus 4 equal to minus 8x plus 7. And we're going to add 8x to both sides, and we're going to add 4 to both sides, and get the x value for that point is 11/14. So C occurs at 11/14, comma, the y value is going to be plug that x value into either equation. I'll do 6x minus 4. So it's 6 11/14 minus 4. And that will turn out to be, after you simplify, 5/7. Okay, so now we're going to get two vectors. We're going to get vector CA, which is the C component, which is basically 11/14 minus 2/3, comma, 5/7 minus 0. So you just take the x component of C and subtract the x component of A. Take the y component of C and subtract the y component of A. Now, if you do this, you should get, after you simplify the denominators and everything, you should get, this one will be 5/42 and 5/7. Vector CB is going to be 11/14 minus the 7/8 and 5/7 minus 0. And if you do that one correctly, you should get minus 5/56 and 5/7. Okay, now that's just to get these two vectors. Now you have to plug it into the formula. So you've got to do, let's see, the one with the angle between them. So we're going to have to calculate theta is the arc cosine of A dot B divided by magnitude A times magnitude B. So, and we're calling this A and this B. So, A dot B, so A dot B is going to be this times this, plus this times this, and you will basically get, after you round, 0.5. Then you have to calculate magnitude of A. So square 5/42, square 5/7, take a square root. Okay, so for the magnitude you'll get 0.724 for A, 0.719 for B. Now you have to take 0.5 divided by those two multiplied and take an arc cosine, and after all of that, you will get approximately 17 degrees between those two vectors. So you can kind of see it in here. I mean, I did draw this to scale. This is not that big of an angle, so that's about 17 degrees. Okay, that's problem 11. Okay, problem 12 is not as bad as problem 11, I promise. It's direction cosines and their angles, and these are not too bad. So the direction cosine alpha is just equal to the I component A divided by the magnitude of the vector. And the direction cosine of beta is the B component of the vector divided by the magnitude of the vector. And the cosine of gamma is the C component of the vector divided by the magnitude of the vector, where this vector we've written as A, B, and C. So all we have to find is the magnitude of this vector. So it's going to be the square root of 4 squared plus 1 squared plus 2 squared, which is the square root of 21. So we just have to take each of these three components divided by the square root of 21. So there's going to be 4 over root 21. There's going to be the second number 1 over the square root of 21. And then the cosine of gamma is 2 over the square root of 21. Okay, so we get those three answers there. And then you have to perform that calculation. So to find these three different angles, you would take alpha is the arc cosine of 4 over square root of 21. Beta is the arc cosine of 1 over square root of 21. And gamma is the arc cosine of 2 over square root of 21. And if you do those three, you should get 29, 27, and 64 degrees respectively. Okay, problem 13, they give us the direction cosine vectors again. But this time our vector is equal in all directions. So it's its magnitude in the x is c, its magnitude in the y is c, its magnitude or in the z direction is c. So the magnitude of this vector is the square root of c squared plus c squared plus c squared, which is the square root of 3c squared. But the square root of c squared is c. The c can dig out of there, so this is c times the square root of 3. That is the magnitude of the vector, which means the directional cosines are just each component c divided by c square root of 3. But the c's cancel, so you get 1 over square root of 3. And that's going to be the exact same for all three direction cosines. Okay, and then all you have to do to find the angles, so alpha should equal beta should equal gamma, will be the arc cosine of 1 divided by square root of 3, and it turns out to be approximately 55 degrees for this particular vector. Okay, problem 13. Okay, and I had talked about how we would revisit this scalar and vector projections, and we'll see a picture here in a minute. So this wants the scalar projection of B onto A, and it gives us two vectors in 3 dimensions. All we need is the equation. So the scalar projection, which we call comp AB, is equal to the dot product between these two vectors divided by the magnitude of the vector it's being projected onto, which in this case is A. So A dot B is going to be 3 times 2 plus minus 6 times 1 plus minus 2 times 1. And the magnitude of A is going to be the square root of 3 squared minus 6 squared plus minus 2 squared. And if we do this, we will get on top, we'll get minus 2 on top. 6 minus 6 goes away, plus negative 2. And then we'll get the bottom, the square root of 49, which is 7. So the scalar projection of B onto A is minus 2/7. Okay, now the vector projection is a little more involved. The vector projection, which we call the projection, PROJ, of B onto A is equal to the scalar projection, comp AB, times, it's going to be the vector A divided by the magnitude of A. But we know this is minus 2/7, and we know A was 3 minus 6 and minus 2, and the magnitude of A was also 7. So we see 7 shows up twice here, and so we're going to get double each of these 3 numbers and apply a negative, so we're going to get minus 6/7 times 7, which is 49. We're going to get minus 2 times minus 6 is positive 12/7 times 7, 49. And we're going to get, oops, I don't need that equal sign there. And we're going to get minus 2 times minus 2, which is positive 4/7 times 7, which is 49. And that should go right here. Yep, looks correct. So that would be the different kinds of projections. Now, I still haven't shown you what this means graphically, but that's what we're going to do in the next problem. Okay, for problem 15, we're given 2 vectors in 2 dimensions. Thankfully, we can draw these. And it wants us to find the orthographic projection of B onto A. So the way we would calculate this is this way. So the orthographic projection of B onto A is equal to B minus the projection of B onto A. So B vector in this one is 4, 6. But we got to find the projection of B onto A. So let's look at that one down here. We just saw this. The projection of B onto A was equal to, we found it using the scalar projection. I'm going to do this all in one equation. It would be A dot B divided by the magnitude of A times A over the magnitude of A. So this is really A dot B over the magnitude of A squared times A. And boy, I have to be real careful. This is not a dot product. This is multiplication. Okay, so A dot B, this is going to equal 2 times 4. So 2 times 4 plus 8 times 6. Now what's nice about this is the magnitude of A squared gets rid of the square root. So it's going to be 2 squared, the components of A squared, but not square rooted. And then we're multiplying this by the original vector 2, 8. Well, this is going to be 8 plus 48 divided by 4 plus 64. Okay, so if you do this arithmetic, you will get 14/17 is what all this simplifies to. Then you're multiplying that into the vector A, which is 2, 8. So you get 28/17, and 8 times 14 is 112/17. Now that goes back up here. And the only difficult part of this is just getting lowest common denominators and making sure your fraction work is correct. But if you do this, you should get 40/17 and minus 10/17. So that's the orthographic projection of B onto A. Now let's see what that means from the picture. Okay, so the easiest one to look at is the answer, which is the bottom left picture. So if you look, B is, let me get rid of that. B is 4 in the x, 6 in the y. So B goes down to 4, 6. So that's how they got that vector B, 4, 6. Now the projection of B, oh, let's do A. A, let's do in green, 2, 8. So 2 in the x, 8 in the y. The intersection of those 2 points is A, right there. The projection of B onto A is like if you shined a flashlight onto B and the shadow would be cast onto vector A. So you can imagine, let's try purple here, if the colors don't bleed over. I shine a flashlight at B, its shadow onto A is going to look like this purple line right here. That's the projection of B onto A. Now the orthographic projection of B onto A is going to be the vector that's perpendicular to A and it goes to B. So let's do that in red. It would be this line right here. That's the orthographic projection of B onto A. Now, the way we drew it, and these numbers aren't great, 40 over 17, which is, okay, so in decimal form, this orthographic vector is 40 divided by 17 is 2.35, and minus 10 over 17 is minus 0.59. So if I were to draw that to scale, this would be 2.35 in the x about here, and negative 0.6 in the y about down here. It would go to right here. So the vector looks like that. Now that's what we found. But what they did was and again, I had talked about this before, you can translate a vector up or down as long as you keep its angle exactly the same. So they just brought this vector up and they attached it to the projection, the purple line, and then you can see how it's going to connect to vector B. So this red vector and this red vector drawn to scale are the exact same vector. They just moved it so you could see this triangle a little better. Okay, so that's problem 15. Okay, the last 5 or so are actually not too bad. Problem 16 says, what's the force, actually we're doing work here. Find the work done by the force. So we had said work as a scalar was force dot distance. Well, if you don't know the dot product, you can do that same equation rearranged and get the magnitude of the force times the magnitude of the distance times the cosine of the angle between these two things. And it just so happens they gave us the numbers for all these. It says the magnitude of the force is 25 pounds. The distance she dragged the sled, so she's dragging a sled, was 70 feet. And the angle between the force and the distance was 35 degrees. So if you take cosine of 35 and multiply by 70 and 25, you'll get the work done by pulling this sled is 1434 foot-pounds. So in English units, forces in feet, or excuse me, forces in pounds, distances in feet. So to get the unit for work, you just multiply those and call it foot-pound. And that's problem 16. Should be fairly straightforward, kind of a plug-in job. Just make sure your calculator's in degree mode.